Chapter 5 was the last chapter of Unit 1, the last chapter of our Alchemy unit. And the title of this chapter was Building with Matter. And the focus of this chapter was twofold. One was to introduce us to classifying matter based on certain specific properties, and that led us into an introduction of chemical bonding. And then we ended the chapter with really looking at the only possible way we could harvest or extract gold. We, up until this point, have found that in chapter 1, we used density to show that through a chemical, really 1 and 2, through a chemical change, gold cannot be created because of the law of conservation of mass, that we would have to start with gold if we want to end with gold. A nuclear change, like we saw in chapter 3, of all the possible ways we were unable to make gold, fusion was our only hope, but that only happens in stars. We can't do that here on Earth. In chapter 4, changing the electrons does not change the number of protons. We can turn an atom into an ion, a cation or an anion, but that's not going to help us make gold if we're not changing the protons. So chapter 5, we're really looking at the only possible way in which we could extract gold if we want to. So we started by testing substances for solubility and conductivity. Solubility meaning will it dissolve in water, and conductivity meaning will it conduct electricity. And we have this flow chart here, which should look familiar because we used this in chapter 5. We said that the substances that dissolved in water, or which were soluble, and conducted electricity had formulas like NaCl and CuSO4. For the substances that dissolved in water, were soluble, but did not conduct electricity, they had formulas like C12H22O11 and C2H5OH. For the substances that did not dissolve, were insoluble, those that conducted electricity had formulas such as Cu and Fe, and then those that did not dissolve and did not conduct had formulas like SiO2 and, for example, C20H42. Now, ultimately, what we did was we looked for similarities, right? It was not a coincidence that all of the substances that conducted and dissolved and then conducted fall under the same bucket here. And all of the substances that dissolved but did not fall under the same bucket. What we came to conclude was that there was a reason they were being sorted as such, and that the substances that dissolved and conducted were actually bonded similarly. Those were ionic substances. The substances that dissolved and didn't conduct were also bonded similarly. They were molecular covalent substances. The substances that did not dissolve but conducted electricity were bonded similarly. They were metallic substances. And the substances that didn't do anything, did not dissolve, did not conduct, were bonded similarly. They were network covalent substances. So we're going to go through and recap what each of those different types of bonding means. We should be able to recognize the bonding type from the formula itself. Remember, ionic is metal-nonmetal, molecular covalence only nonmetal, metallic is only metal atoms, and then network covalent is hard to distinguish sometimes between molecular covalent, but there are a few network covalent substances you should be familiar with. So for ionic bonding, the description of that bonding type is that metal atoms give up or lose their valence electrons to the nonmetal atoms. So we have a transfer of electrons here from one atom to another that creates positive and negative ions that then attract to each other in this alternating crystal lattice, right? Just like this. Those substances will dissolve in water. The water molecules will pull apart one cation from another anion and move them apart from each other, just like up here shown with the NaCl. They will conduct electricity only when dissolved. So an important property for ionic substances is that as a solid they do not conduct electricity, because for electricity to flow through a substance there needs to be moving charge. The charge can be an ion, it could be electrons, but there needs to be some form of moving charge if electricity is going to flow through a substance. And in a solid ionic compound, while there are charges, because there are ions, they're locked in place because they're strongly attracted to each other as a solid. Only when they have been dissolved in water are they free to move independently from one another because the water pulls them apart, and that's why electricity is able to flow through aqueous ionic compounds. As solids, they are brittle, and they are made of metal and nonmetal ions combined together. For substances that are metallically bonded, remember that the bonding depends on the position or what the valence electrons are doing. So in ionic bonding, or in a substance that is ionically bonded, we have electrons that were transferred to create cations and anions that attract together. In something that's metallically bonded, we have the valence electrons from all of the atoms that leave their atom and roam from one atom to another. We call them delocalized electrons. And those delocalized electrons are free to roam from one atom to another throughout the entire substance. These substances don't dissolve in water. The bonding is too strong, right? All of the electrons at once are sort of acting like this really strong glue that holds all the atoms together. Because they have free-flowing electrons in a solid, the electricity is able to flow through metallic substances in the solid form. They are malleable, which means we can bend them, but they're fairly hard. They're not soft, like they're not going to melt in the palm of your hand. And they're made entirely of metal atoms. That's how we'll recognize it from the formula. In something that's molecular covalent, remember, covalent means sharing valence electrons, and molecular means that the atoms are sharing electrons to form discrete identical units. We call those molecules. So valence electrons are shared between atoms. This creates small stable units called molecules within a substance. Remember, a molecule, we can only use that term if the atoms are covalently bonding. So I wouldn't call NaCl a molecule, I wouldn't call copper a molecule, but I can call water a molecule, I can call CO2 a molecule, I can call methane a molecule, because the unit that we're calling a molecule has to have atoms that are covalently bonding to each other. In these types of substances, some dissolve in water and some don't, and we went over a rule actually in chapter 8 that helps us determine it's like dissolves like. So it was based on polarity. If the two substances have similar polarities, they will dissolve. If not, they won't. So water is a polar molecule, so the only molecular covalent substances that will dissolve in water are other polar substances. We'll go over polarity and how to determine that in the chapter 8 review video. Molecular covalent substances do not conduct electricity in any way, shape, or form because there's no free-flowing charge in their compounds, not electrons, not ions. They exist as solids, liquids, or gases at room temperature, and they are made entirely of nonmetal atoms. That's how we'll recognize it in their formula. Network covalent bonding, we have some similarities here. It's covalent. They're still sharing valence electrons, but they're sharing to form not individual molecules, they're sharing to form an extensive network. So where this shading is occurring, we're seeing that the atoms are sharing electrons with each other, but they're sharing throughout the entire substance, right? There's no one smaller discrete molecule I can circle like I did here. This entire thing is the molecule, so we call network covalent substances exist as what we call a macro molecule. And it's hard to determine by the formula because these are made of entirely non-metal and/or metalloid atoms. There are a few that we went over that you should be familiar with though. SiO2, which was sand or quartz. We have diamond, which is carbon. And then we have silicon. So if you know those three examples as being network covalent, those are the only three network covalent substances you will ever see. Everything else, if it has non-metals, would be considered for our level a molecular covalent substance. Network covalent substances don't dissolve in water. Their bonding is way, way too strong. It's the strongest type of bonding because of how extensive the network of covalent bonds is. They don't conduct electricity because there's no moving charge. Again, no free moving electrons, no free moving ions, and they are extremely hard as solids, hence diamond, quartz, sand. The last bit of information that we went over was electrolysis and electroplating. So electrolysis is the process of extracting a metal element from an ionic compound containing that metal. And electroplating is using electrolysis to coat a metal on the surface of another element. Now, electrolysis was really our only hope of harvesting, quote unquote, harvesting gold. If I have an ionic compound that contains gold, I can pull that gold out of the compound, but I have to do it using the process of electrolysis. And we did a lab where we actually dissolved some copper 2 sulfate solution, or some copper 2 sulfate solid in water to make a solution, and then we used nickel wire. We hooked up a battery to it, and we saw that the copper started to coat along this nickel strip. And we said what was going on, because in this solution, when we dissolve the copper 2 sulfate, the water splits apart the ionic compound into 2 ions that make it up. So we have Cu+2 cations and sulfate anions. From the negative end of the battery, electrons come out, and they will flow along this wire, and the electrons start to coat on the nickel wire or the nickel strip. And the copper ions, being positive, are attracted to those electrons, and they will take those electrons in a process we called reduction. Reduction is when an atom or an ion gains electrons. When this copper ion gains 2 electrons, it will turn back into a neutral copper atom, meaning elemental metal copper. That's what we saw start to coat on the surface of the nickel strip. So that process of extracting the copper from the copper sulfate is called electrolysis. The act of it coating on the nickel strip is what we call electroplating. The important thing to understand here is that we can do this with really any ionic substance. In this example here, we have zinc chloride solution. So in this solution, we have zinc plus 2 ions and Cl-1 ions. If we want to extract the zinc metal, the zinc ion is not zinc metal. It's a free-floating ion in the solution. We have to provide it with electrons to turn back into the metal. And because it's a +2 ion, we have to provide it with 2 electrons to reduce it back into neutral zinc so that it becomes a metal again. In the solution of gold here, it exists as a +3 ion. So if we want to extract the gold as metallic gold, elemental solid gold, we have to provide that gold ion with 3 electrons, so it will take those 3 electrons and turn back into neutral gold. So we ended here with saying that this is really the only shot we have at extracting or harvesting or quote-unquote making gold. We can't make it out of nothing. Nuclear reactions on Earth are not feasible, but we can take the gold that already exists here in compounds and extract the element using the process of electrolysis, which is really just running electricity through a solution of a gold-containing ionic compound, providing the gold ion with the number of electrons necessary to reduce it back into a neutral gold atom, and then we can collect the solid gold from there. So this is the end of chapter 5, which was building matter, and the end of our unit 1, which was alchemy.